Hello and welcome to another video. This video would be a continuation of the previous video on the Laplace transform and the inverse Laplace transform. So in the previous video we had seen until 3. So today we will see the inverse Laplace, how to derive the inverse Laplace for 1 by s plus 3 the whole square first. So to find the inverse Laplace transform of 1 by s plus 3 the whole square, we will be using the frequency shift theorem. So in the last video we have seen what is frequency shifting theorem. So when you multiply our function f of t with e raised to minus at, in the frequency domain it is a shift. So that is why it is called a frequency shifting theorem. Wherever s is there, we will replace that with s plus a. And the Laplace of t u of t is 1 by s square. So Laplace of the combination of these two, Laplace of e raised to minus at multiplied with t u of t. So t u of t is 1 by s square. So this part is 1 by s square. And when you multiply our function t u of t with e raised to minus at, you will replace, wherever s is there, you will replace that with s plus a. So it is 1 by s plus a whole square. So the Laplace of e raised to minus at t u of t is 1 by s plus a whole square. So here our function is 1 by s plus 3 the whole square, and the inverse Laplace of that would be, so here when you replace a with 3, you will get 1 by s plus 3 whole square. So the inverse of that would be replace a with 3. So e raised to minus 3t t u of t. That would be the inverse Laplace transform of 1 by s plus 3 whole square. So this is how we use frequency shifting theorem to get the inverse Laplace of this function. Now we will find the inverse Laplace of 2 by s plus 1 into s plus 2 the whole square. Here there is a speciality that the roots of the denominator are real and repeated. So the roots of this denominator is minus 1, minus 2, minus 2. So the roots are real and repeated. The denominator root at minus 2 is a multiple root of multiplicity 2. So each multiple root generates additional term consisting of the denominator factors of the reduced multiplicity. So that means we will replace this. As I mentioned earlier, each multiple roots generate additional terms. This is the additional term consisting of the denominator factor of reduced multiplicity. So the multiplicity is reduced from 2 to 1. So if this was a factor of 3, then it would have been 2 and then again with a 1. So now for the first two terms, it is easy to find what are the values of k1 and k2. Let us find that. So to find k1, we will multiply our function 2 by s plus 1, our actual function 2 by s plus 1 into s plus 2 whole square into s plus 1. We will multiply with s plus 1 at s equal to minus 1. So we can cancel this off and substitute. When we substitute s equal to minus 1, we will get the value of k1 as 2. Now to find k2, again, we will multiply our function 2 by s plus 1 into s plus 2 whole square with s plus 2 with the denominator s plus 2 the whole square. And this both will get cancelled and substitute s equal to minus 2. So here, when you substitute s equal to minus 2, we will get the value of k2 as minus 2. Now the challenge is to find the third, k3. So to get the value of k3, right now we have got the value of k1 and k2. So k1 is 2 by 2 and k2 is minus 2. So this is right now the partial fraction expansion. To get the value of k3, we will equate both left and right hand side. So you multiply this term, whole term, you take this whole term to this side. So it will be 2, the numerator 2 the numerator 2 equal to 2 into s plus 1 whole square minus 2 into s plus 1 k3 into s plus 1 into s plus 2. Now when you multiply this, when you expand this right hand side, you will get 2s square plus 8s plus 8 minus 2s minus 2 plus k3s square plus k3s plus 2k3. So I'm equating all the constants on the left hand side and the right hand side. So here you have 8 as a constant, here you have minus 2 as a constant, and another constant is 2k3. So when you equate that, you will get the value of k3 as minus 2. Similarly, you can also equate the s square, coefficients of s square terms. So when you take the coefficient of s square on the left hand side, it is 0. So on the right hand side, you have the coefficient 2 and k3 s square. So here you can equate, this is got by equating the coefficient of s square. So on the left hand side, there is no coefficient for s square. On the right hand side, you have 2 and k3. So you get the value of k3 as minus 2. The result can also be obtained in two other ways. First is by equating the coefficients of s, another is by equating the coefficients of constants. So when you equate the coefficients of constants, it is, the constant is 8 minus 2 and 2k3. On the right left hand side, you have the coefficient 2. So you will get k3 as minus 2. Or you can equate the coefficients of s on the left hand side, and on the right hand side, you will again get the value of k3 as minus 2. So whichever is simpler for you, you can equate that and find the value of k3. So now you got the value of k3 as minus 2. Now to get, as we have seen in the beginning of the video, to get the Laplace of this, we had used frequency shifting theorem. So similarly here, 2 by s plus 1 will have inverse Laplace as 2 e raised to minus t, and minus 2 by s plus 2 whole square will have the Laplace as t e raised to minus 2t. This is by frequency shifting theorem. And the third term 2 minus 2 e raised to minus 2t. So this is the inverse Laplace transform for this. Now we will see the third case where we have the roots of the denominator as a complex imaginary term. So when you find the roots, you will have complex or imaginary terms. So to find the inverse Laplace of this function, we will split that. We will expand by partial fraction expansion. So for this, with imaginary roots, we will have to write it like this: k2s plus k3. So k1 by s plus k2s plus k3 by s square plus 2s plus 5. So k1 can be easily found by multiplying our total function 3 by s into s square plus 2s plus 5 into s. So we can cancel this s and s at s equal to 0. So since the root of this is 0, s at s equal to 0. So 3 by s square plus 2s plus 5 at s equal to 0 will give you the value of k1 as 3 by 5. So next, to find k2 and k3, we will equate the numerator and the denominator. You will equate the numerator on the both sides. So you will multiply this denominator on the other side, and you will equate both numerators. So 3 equal to k1, that is 3 by 5, into s square plus 2s plus 5, k2s plus k3 into s term. So the s square plus 2s plus 5 will be cancelled by this. So k2s square plus k3s. So we can equate the terms by substituting k1 equal to 3 by 5, which we found earlier. So after equating, it will be k2 as minus 3 by 5 and k3 as minus 6 by 5. So we will write the partial fraction expansion for 3 by. We will write the partial fraction expansion for 3 by s into s square plus 2s plus 5. So it will be 3 by 5 by s minus 3 by 5 s plus 2 s square plus 2s plus 5. Now the last term is shown to be as the sum of Laplace transforms of exponentially damped sine and cosine. So the Laplace of a e raised to minus at cos omega t. So that would be a s plus a by s square plus a whole square plus omega square. Since Laplace of cos omega t is s by s square plus omega square, when we multiply e raised to minus at, we have frequency shifting. So wherever s is there, we will replace it with s plus a. So that is how you get this. Similarly, Laplace of b e raised to minus at sine omega t will be b omega by s plus a whole square plus omega square. So there again, there is frequency shifting. By multiplying e raised to minus at, you will replace wherever s is there, s plus a. Now the combination of these two equation for Laplace of e raised to minus at, the combination of this first equation and the second equation would be Laplace of a e raised to minus at cos omega t plus b e raised to minus at sine omega t would be a s plus a plus b omega divided by s plus a the whole square plus omega square. The denominators are same. Now when you compare this term with the term that we have, we will see that there is some similarity. So we will adjust the terms in the numerator without changing its value. We will get, now I have adjusted this numerator without changing this value. So it is still s plus 1 plus 1, that is s plus 2. So it is of the same value. I just made some rearrangement. So this now looks similar to this Laplace function. So where a, the value of a is 1 and the value of omega is 2. The value of b is 1 by 2. The value of capital A is, sorry, the value of capital A is 1. The value of capital A is 1. So now the inverse Laplace transform of the first function is 3 by 5 and the inverse Laplace of second function is 3 by 5 e raised to minus t cos 2t plus 1 by 2 sine 2t. So this we got from this inverse Laplace. So this is the Laplace inverse of this function. So now we will move on to finding the Laplace transform of a differential equation, which is given below, and to solve for y of t for all initial conditions as 0. So this is a step towards one of the important topic, the transfer function. So we will see that in detail in the next video, but this transfer function is got from here. So by taking the Laplace on both sides, so Laplace here and Laplace here. Now we have taken the Laplace of the second derivative, so it will be s square y of s. They have given that the initial conditions are 0. And for first derivative, the Laplace would be s into y of s, and you multiply it with the coefficient 12. And for the third term, 32 y of s. The right hand side, you have 32 by s. So the Laplace of u of t, the step function, will be 1 by s. Now keeping y of s on the left hand side and taking all other terms on the right hand side, you will get 32 by s into s square plus 12s plus 32. So that is nothing but 32 by s into s plus 4 into s plus 8. Now by partial fraction expansion, we will split this equation as k1 by s plus k2 by s plus 4 plus k3 by s plus 8. To get the value of k1, we will multiply the total function into s and substitute the value of s equal to 0. So we will get, after substituting s equal to 0, we will get the value of k1 as 1. we will get the value of k1 as 1. So to get the value of k2, we will multiply the total function 32 by s into s plus 4 into s plus 8 with s plus 4. Can cancel that off and substitute the value of s equal to minus 4. So you get the value of k2 as minus 2. Similarly for k3, you will multiply the total function 32 by s into s plus 4 into s plus 8. With s plus 8, you can cancel that off and substitute the value of s as minus 8. You will get k3 as 1. So you will get y of s as 1 by s plus minus 2 by s plus 4 plus 1 by s plus 8. And the inverse Laplace of 1 by s is 1, minus 2 by s plus 4 is minus 2 e raised to minus 40. 1 by s plus 8 is e raised to minus 80. So y of t equal to 1 minus e raised to, so Laplace of y of s is 1 by y of t. No, this is what they have asked. Solve for y of t if all initial conditions are 0. So y of t equal to 1 minus 2 e raised to minus 40 plus e raised to minus 80. So this is how you find the value. So now here it was in time domain. We had converted it to the frequency domain. And then finally this step we have converted it back into the time domain. So the analysis in the frequency domain was easier compared to that in time domain. So we are solving for y of t if all initial conditions are 0 for this differential equation. Thank you.